I'll let everybody in.
Maybe we wait 1 more minute and then we start. Okay, I think we can start probably. Well, good afternoon, everyone, and welcome to the next talk of the Data Science of Graph seminar, which is given by Jian Tang. First of all, thank you for accepting to give us the talk. It's a great pleasure to have you here. A quick introduction about Jian. So he's currently an assistant professor at Mila Quebec AI Institute, and also at the Computer Science Department and Business School of University of Montreal. He is a Canada CIFAR AI Research Chair, and his main research interests are on graph representation learning, graph neural networks, geometric deep learning, deep generative models, knowledge graphs, and draft discovery. He's the recipient of many awards, including the Best Paper Award in ICML 2014, Best Paper Award in WWW 2016, but also in 2020, he was awarded the prestigious Amazon and NSN Faculty Research Award. Of course, he has a lot of representative papers and very well-cited papers in the area of graph representation learning. And currently with his team, recently they have released also an open source machine learning package called TorDrug, aiming at making AI drug discovery software and libraries freely available to the research community. So we hope to listen about some of these things today in this talk. And yeah, thank you again. And the stage is yours, I guess.
Thanks, Doreen. Yeah, go ahead.
Just for the people who, for the questions, I would say that as usual, we keep it for the end. But if there is any urgent, quick question, you can write it in the chat or you can unmute yourself. But let's try to keep them for the end of the talk. Thank you.
Okay. Thanks, Dorina, for the nice introduction, and also thanks a lot for the invitation. It's a great honor to speak here. So I'm going to talk about our recent work on geometric deep learning for drug discovery. So maybe I can start with an introduction on drug discovery. So for drug discovery in general is actually very long and also expensive process. So in general, so if we want to develop a new drug, it takes more than 10 years and costs like $2.5 billion US. And so usually a typical process of like drug discovery is like this. So we have some target. So most of the time is a protein or an enzyme. And then, so we're gonna get into the stage of drug discovery. Basically in this stage, we're gonna discover some drug candidates. So usually we will first identify some hits. Maybe we have like thousands here or hundreds here. And then we're gonna further select some lead candidates from the hits, maybe tens of like molecules. And then we further trying to optimize the properties of those leads, because for some of the molecules like selected in the second in this stage, so they are not ideal. For example, they may have like their binding affinity may not be strong enough. The toxicity could be high, right? So we need to do some optimization in order to further improve the properties of the drug candidates. So, and then later, these candidates will be sent into preclinical trials. Like basically, we mainly evaluate those like candidates through on animals. So if they're able to pass the preclinical trials, they will be able to further send to the clinical trials for evaluation or validation. So in general, this is really like a very long process and really expensive. And for us, we mainly focus on the first stage using machine learning methods to discover new drug candidates in a more efficient way or more effective way. Okay, so that's our goal. So now we actually see a big opportunity for AI to accelerate the process of drug discovery. So the main reason is that now we really have a huge amount of data in the biomedical domain from a few different sources. For example, scientific literature. So a lot of like papers are published in PubMed, in bioRxiv, and there are also some like a public database, patents, clinical trials, and also now thanks to the recent progress of like next generation sequence, we actually are able to have like some very high throughput by assays. So we are really able to generate a lot of data. So with so much data, then we can really leverage AI techniques to analyze those data to build predictive models, for example. So we can build predictive models basically to predict the properties of the molecules, so then we can really like keep the molecules that are most likely to succeed in the clinical trials. So here, let me show you one example, maybe not on small molecules, but actually on antibodies. So this is an antibody discovered by the company Absera. So they use their AI techniques to find lead antibody actually within 3 months for treating the SARS-CoV-2 disease, right? So this is really quick. So previously this could take like 2 years, but with AI techniques, this is really quick. Right? And then, so here we talk about like data, right? So we have a lot of data in this domain, but then you may wonder what kind of like specific data we care about in this domain. Of course, this is actually not surprising. So we mainly care about actually a few different type of data. The first type of data is like small molecules and also proteins, right? Depending on which kind of drug you want to develop. But for both like small molecules or proteins, so they can be represented as graphs. So for small molecules, each node is an atom. So the edges between the nodes are the bonds between the atoms. Okay. So this is for small molecules. So for proteins, so usually, so there are a few different ways to represent proteins. So we can either treat each residue as a node, and then we can use a spatial distance between the residues as edges between the nodes, right? So that means that we can also represent the proteins as a graph. Okay. Of course, actually, for both small molecules and proteins. Instead of like represent them as graph, a more natural solution representation would be their 3D structures. Basically, we just like represent all the atoms as their 3-dimensional coordinates, right? So that means we can represent both small molecules and proteins as a 3D structures, right? And this is one type of data, small molecules and proteins. So we can either represent them as graphs or 3D structures. Okay. So another type of like data which are very important in biomedical domain or in drug discovery are biometric knowledge graphs. So what are biometric knowledge graphs? So biometric knowledge graphs basically encode the complex relationship between different kinds of like biometric entities. For example, drugs, disease. For example, this drug can be used to treat this disease. And also genes, for example, this gene is a causal gene of this disease, right? And this drug can somehow block this gene or proteins, right? So basically, you can see like biological graph, like really like is a very effective way to encode like a large number of like facts in the biomimetic domain. So they are very useful in a bunch of applications in drug discovery, for example, drug repurposing or target identification. Okay, so you can see like then. So these are the main data we care about in drug discovery domain. And then the question is, how can we use AI techniques, in particular different techniques, to analyze those data, right? So then that's why we need to develop geometric deep learning. So what are geometric deep learning techniques? So geometric deep learning techniques are techniques so refer to general techniques which are used to model data with irregular structures, for example, graphs, 3D structures, 3D point clouds like molecules, proteins, right? Biometric knowledge graph. So there are really like a bunch of techniques that have already been developed in this area. For example, knowledge graph embedding or knowledge graph repetition techniques, which are used to learn the repetitions for knowledge graphs or for biometric knowledge graphs. So we also have graph neural networks to model graph data, for example, molecules, right? And then now we really have like these are really like geometric deep learning techniques. So which are deep learning techniques are developed to model 3D structure data, right? Like say molecules, right? When we try to represent molecules as 3D structures, and then we can use geometric deep learning techniques to model their 3D structures. For example, we can use geometric deep learning techniques to model the surface of proteins, so which are very important when we try to model the functions of proteins, right? So all these techniques in general we call them like geometric deep learning techniques. Okay. So next I'm going to show you like how we use like geometric deep learning techniques to some important applications or problems in drug discovery. So the first type of problem we focus on is like de novo small molecule drug discovery. So here we actually focus on a very few important problems in this area, in this domain. The first one is like molecule property prediction. So basically, given a molecule or given compound, so we try to predict their properties. For example, we want to predict their binding affinity, the toxicity, right? So this is the first type of problem we want to solve here with machine learning, with graph neural networks. And once we have like a machine learning predictor for the property, and the next question we care about is we want to find the molecule with optimized properties, right? We want to do a search space. We want to search in the entire chemical space to find the molecules with design properties. And the second problem, that's why we focus on like de novo molecule design and optimization. So basically, I said we want to, based on the machine learning predictor of the property predictor, which can be used as an oracle or as a reward function. So this can guide us to find the molecules with optimal properties. So this is the second problem, de novo molecule design and optimization. Okay, let's say through this process, we already find this molecule. However, this molecule in practice, they may not like exist, right? And then the third problem we care about like is retrosynthesis prediction or planning. So basically, so we have to think about like how are we able to synthesize this target molecule structure based on the existing ones, right? So here, basically, given a designed molecule structure, we want to identify a set of like reactants which are able to synthesize our designed molecular structure. Okay, so this is the third problem we want to solve. Okay. And the second type of like a research problem we want to address, we want to like work on using geometric deep learning is like drug repurposing. So instead of like discovering totally new drugs, so another way to find the drug to find like a disease treatment is called like drug repurposing. So basically, given a new disease, so we want to see which existing approved drugs could be used to treat the new disease. For example, when SARS-CoV-2 first show up, right? So it could be very difficult to find to develop totally new drug in the very first beginning. So then a better solution would be really to see whether some of the existing approved drugs they can be used to treat this new new disease, right? So that's called like drug repurposing. So mathematically, or even from the point of view of machine learning, so essentially this problem can be formulated as a link prediction on biometric knowledge graph. So as we just discussed, so biometric knowledge graphs encodes the complex relationships between drugs, disease, and proteins. And then, so essentially what we want to do here is we want to predict whether there will be a link between a drug and the disease. So if there's a link between a drug and the disease, that means this drug could potentially be used to treat this new disease. So that's the essential idea. Okay. So let me mainly focus on the first type of like research problem, de novo drug discovery. So I'm going to introduce each of the three problems like briefly. Okay. The first one is like predicting the molecule property using machine learning techniques. Okay. So in practice, we know like if you want to like make very good prediction, so then the fundamental problem here is how are we able to learn very effective representation of molecules? And so as we discussed in the beginning, so we can represent molecule as a graph. So then the problem is how can we learn good graph representation, right? So this is not surprising. Usually people just use graph neural networks. So graph neural networks basically, so there are quite a few like different variants of graph neural networks out there in the literature. For example, the vanilla graph convolution networks or graph attention networks. But in general, all these different kinds of architectures can be summarized into the paradigm of neural message passing between the nodes. So let me give you an example that maybe you can understand the basic idea. Suppose here we have graph, okay, and then so graph neural network basically tells you a way to iteratively update the node repetitions. So basically, one layer of graph neural network will allow us to update the node repetitions. Okay, so you have multiple layers of graph neural networks. Then we're gonna update the node repetitions multiple times. Okay, then the question is how do we update the node repetitions in each iteration? Okay, so here's the example. Let's say we is our central node. Okay. And then what we have here in the graph neural network architecture or in general neural message passing framework is that so we usually have a function called like message passing, so which determines the messages from the neighbor. Okay, so here the message function is actually defined on each edge. Okay, so this function or this small neural network depends on the HWK is the source node, okay, the rotation of the source node. So HVK also depends on the rotation of the target node, as well as the features on the edges. EVW corresponds to the features on the edges, right? So with this massive passive function, then we know, okay, what kind of like messages we should receive from each neighbor, okay? So we're going to receive message from each neighbor. Then the next question is, because we have many neighbors, right? So then how do we aggregate the messages from different neighbors? And then we have an aggregate function here to aggregate the messages from different neighbors. So a simple aggregation function could be like just take summation. Basically, you sum up all the messages from your neighbors, okay? And then you have your message from neighbors. But of course, like for the node V itself, it has also a repetition. So the next question is, how can we combine the messages from the neighbors, which is the MVK plus 1. K here is the index of the layer, for example, case layer of graph neural network. Okay, so we're gonna combine the messages from the neighbors with the current node repetition. So by doing this, so we can get a new repetition for the target node. Okay, so we can do this for this node. We can do this for every node on the graph. So in one iteration, but then we can do this iteratively. So by using different layers of graph neural network. So you can see that with different layers of graph neural networks, we basically going to iteratively update the node repetitions. But remember that at the end, we don't care about the. So our goal is not trying to learn a repetition for each node, because we actually care about the repetition of the entire molecular graph. And that's why at the end, we usually have to have a readout function. Basically, we try to read out the repetitions from all the nodes to get the repetition of the entire graph. For example, the repetition of the entire molecular graph. Okay. So usually sometimes the readout function will be also very simple. Basic just take summation of all the node repetitions to get the repetition of the molecular graph, right? And then once you have these, and then you can make predictions, predict the properties, and then eventually you can do backpropagation to train the entire neural networks. So that's the essential idea. However, so this is very classical methods for molecular property prediction. However, for this kind of methods, usually we need to provide some label data, right? So you need to provide a set of molecules as well as their activities or their properties, right? So, however, one big limitation in drug discovery is that usually it's very expensive and also time-consuming to obtain the label data, and that's why in our work we focus on the unsupervised or semi-supervised setting. So basically, we try to leverage the unlabeled molecules to learn effective molecular repetitions, right? So this algorithm is called Infograph, which is published in last year's ICLR. So let me give you a little more details. So the essential idea of Infograph is trying to maximize the mutual information between the whole graph repetition, the whole molecular graph repetition, and also all the substructure repetition. So the reason we want to do this is we hope that the whole graph repetition is able to capture the most important information among all the substructures. Okay, so this is the essential idea. Then the question here is how can we define the substructure repetition as well as a whole graph repetition? So this is not too difficult because we can actually use graph neural networks. So what we do here is we use k-layer graph neural networks. So HVK here is the repetition of node V in the case layer. Okay, and then what we do is that we first summarize all the local structure information at every node I by concatenating the repetition of this node in different layers, because the repetition of each node in different layer basically capture different local neighborhood structure, right? For example, in the first layer, just the repetition of the node itself. In the second layer, maybe we also include the first order neighbors, and the second layer we also have the second order neighbors, and that's why by concatenating the repetition of this node in different layers, so we can basically sort of summarize all the local structure information centered at this node. Okay, and then so once we have this, we want to further get the repetition of the whole graph. So we can further have a readout function to get the repetition of the whole graph. Okay, so that's the essential idea. And then the next question is, how can we maximize the mutual information between the whole graph repetition and also the substructure repetition? So here we have a mutual information maximization between the two repetition. So we do this for each node in the graph, of course, and also for each graph in the training data set. And for maximizing the mutual information between the two, we use some JSON-Shannon mutual information estimator. So it looks very complicated, but it's actually very related to some recent very popular contrastive learning techniques. So let me give you an example. Suppose now these are our input molecule, which has 3 atoms, and then so we can use let's say we can use 3 layers of graph neural networks to get the repetition for each node, and then we can concatenate the repetition in each layer to get the node repetition, basically summarize the local structures centered at that node. For example, this is H5 mu, and then we can further do a readout function to get the repetition of the whole graph. Okay, and then basically we train a discriminator, so we treat the whole graph repetition and also the substructure repetition from the same graph as a positive pair. So this is a positive pair. But then how can we construct a negative pair? So we just take a substructure repetition from a different molecular graph in the training batch, and then combine this one with this whole graph repetition. So the two, they are from different graphs. So they are treated as a negative pair, right? And then we train the discriminator to distinguish the positive pair and the negative pair. And then by doing this, we can train our graph neural network, or we can train our graph encoder. So that's the essential idea. So we compare our algorithm with some classical methods for graph for unsupervised graph repetition learning, for example, including those like graph kernel based methods, and also like this is pretty much like node embedding based methods, or some simple methods for graph embedding. So at that time, so our algorithm is able to outperform all these algorithms. Of course, because this algorithm is relatively now old, so there are new methods which are able to outperform our methods, but our methods is still relatively like stable, like on different data sets. Okay. So this is the first work about like a molecule property prediction in self-supervised way. Okay. So the second one is about like de novo molecule design and the optimization. As I said, like in this case, we try to design a molecule with optimized properties. I see a question here. What is an aggregation function? What is a combine function? So aggregation function is simply trying to aggregate the messages from different neighbors. Okay. And the combine function try to combine the messages from the neighbors with the information of the node itself. Okay, so that's the difference between the two. Okay. So we propose a new algorithm called like a graph AF for molecular graph generation and optimization. So the essential idea of graph AF is we formulate graph generation as a sequential decision process. So basically, in every step, we're going to generate a new atom. So let me give you one example. So let's say in the beginning, we start from an empty graph, and then at every step, we're going to generate a new atom. For example, in the first step, we generate a carbon, and in the second step, we generate an oxygen. But besides generating a new atom in every step, we also need to determine the bonds between the newly generated atom with the existing ones. For example, we have to determine, okay, there's a double bond between the two, right? And then in this stage, let's say, so we generate a carbon, so we need to determine, okay, what is the bond between this carbon with this carbon? There's a single bond. What is the edge between this carbon with this oxygen? Okay, there's no edges between the two, right? So we can continue this generation process until like for the newly generated atom, so there are no edges between the newly generated atom with the existing ones. So in this case, we stop the generation process. So this is for the inference. Okay, and then for the training, basically we use the sort of like autoregressive flow for the training. So the essential idea is like we basically you can see like we represent a graph as a sequence of nodes and edges, and these are our observation data, right? And then so we define an invertible mapping from a base distribution, which is usually a Gaussian distribution, to the observation data, which is our graph or a sequence of nodes and edges. And then we use normalizing flows to learn the mapping between the noise distribution and the real world observation. So during the inference, then what we do is like we random sample some noise variable from the noise distribution, and then using the new network. So this noise distribution will map to the real world observation, real world molecules. So that's the essential idea. Okay. So let me show you some experimental results. So we train our model on zinc 250K dataset, which contains around like 250K drug-like molecules. So the largest like molecule contains 38 atoms. And there are 9 atom types and also 3 edge types. So we compare our algorithm with a bunch of different like joint models on the different metrics. For example, the validity metric basically measures whether the molecules are chemically valid or not. So this is the first metric, which you can see that our algorithm is able to generate 100% valid molecules. So uniqueness means like whether the molecules generated by the algorithm, they are different from each other, which is pretty much like all of the case. And novelty, which means like whether the molecules generated by the algorithm, they are different from the training data, which show that like all the molecules generated by the algorithm are different from training data. Okay. So basically through this stage, so we can see that like our algorithm is able to generate valid realistic molecules and also new molecule. Okay. But however, of course, in practice, our goal is not only trying to generate like new molecules, valid molecules, right? Because our goal is trying to find molecules with optimal properties, for example, with good binding affinities or low toxicity, right? And that's why, so here are some examples of the molecules generated by our algorithm. And that's why, so in the second part, we try to develop algorithm which is able to maximize the properties of the molecules generated by our algorithm. So this task is called like a goal-directed molecule generation. So we use reinforcement learning because this is essentially a search problem, right? Okay. And what we did here is like we just fine-tuned the generation policy trend in the first stage with reinforcement learning, and we try to optimize the properties of the generated molecules. Because here we talk about reinforcement learning, maybe you want to know what are the states, actions, and rewards, right? So state is pretty much like the same here, right? So state here is like, for example, the current graph substructure is a state. What are actions? So actions either we try to generate a new atom, or we try to build an edge between the new atom with one of the existing atoms. Okay, so these are the action space. And then in terms of reward, this is also not difficult to design, because our goal is really trying to find molecules with optimal properties. And then we can simply treat the properties of the final molecules as the final reward. Okay. Of course, we can also define other reward, for example, because as end, we have to find, of course, we need to find the chemically valid molecules, right? So we can use the chemical validity as the final reward, of course, as the intermediate reward as well, because during the generation process, we also hope the substructures generated by the algorithm to be chemically valid, right? Okay. So here we evaluate our algorithm on two properties. One is P log P, and another one is drug likeness. So we compare with different algorithms by basically we use the top the best three molecules generated by different algorithms. We compare them, so we can see that compared to other algorithms, our algorithms are able to find molecules with optimal properties for both properties. Okay. So here are some examples of the molecules generated by our algorithm for the two property. Okay. Of course, here you may find it weird, because you can see like if you want to like maximize the P log P property, so you will find molecules which are like trend-like molecules, which is a little bit weird, right? So the reason is that because in both cases we only try to maximize maximize a single property, and that's why in practice actually a more reasonable setting is doing like a multi-objective, multi-property optimization. Basically, if you want to find an ideal drug candidate, this candidate has to satisfy multiple constraints, or they are optimal in multiple properties, right? So that's actually some also in general future direction we are very interested in. Okay. And then actually besides like generating a new molecule from scratch, so another setting is called like a constraint optimization. So basically, in this case, we try to optimize an existing molecule. Let's say here is we already have a molecule which could be the lead molecule, right? So the property of this molecule is not good, and then we can further use our algorithm to make some small modifications to improve the properties of this molecule. Let's look at this example. So by making some really like small modifications, you can see that our algorithm is able to significantly improve the property of this molecule. So this is a second problem, which is about like searching for the molecules with desired properties, right? And once we have a molecule, and then our goal is really trying to, okay, can we find some reactants to synthesize this molecule? Okay. So essentially, so the retrosynthesis prediction can be formulated in this way, right? So we have a target molecule. We try to find a set of like reactants which could be used to synthesize this molecule. And mathematically, we can actually formulate this as a mapping from a graph, because the input molecule is a graph, mapping from one graph to a set of graphs, right? Because each graph in the output correspond to a reactant. And that's why we developed a new framework called a graph-to-graph framework for retrosynthetic prediction, right? So basically trying to map the input product molecular graph to a set of a reactant graph. Okay. So the essential idea of this graph-to-graph framework actually is a two-stage framework. So what we did in the first stage is called a reaction center identification. Basically, we need to determine the reaction center between the two reactants. If there, for example, there's some reaction between the two molecules, and then maybe they will find a new edge between the two, right? And then what we need to do is we just need to determine, okay, where the reaction happens. And then once we identify the reaction sentence, and then we are gonna break this bond, and then we're gonna divide the molecules into two sub-molecules, right? Which we call them synthons. Of course, these two molecules, these two synthons, they are not complete molecules. And that's why we need to have the second stage called graph translation or graph completion. So basically, we're gonna translate each or we're gonna map each of the incomplete synthons to a complete reactant. And we do this for each synthon here, and eventually, and then we can map the input product molecular graph to a set of a reactant graph. So that's the essential idea. Okay. So I will not go into the details due to the time limit. Okay. So these are the first research problem we have been working on, which is de novo drug discovery. So I'm going to briefly mention the second part, which is about drug repurposing. So as I said in the beginning, so essentially, we are trying to predict the links between the drugs and the disease using biometric knowledge graph. Okay, and maybe you wonder why this is useful, and what is the intuition? So the intuition is like this. Let's say, for example, if there's a new disease and there's another disease, let's say this is SARS-CoV-2 and this is SARS-CoV, right? And maybe this disease, there's a link between this drug with another disease, another similar disease, right? For example, there's an old drug which is developed for SARS-CoV-1. So because the two diseases, they are very similar to each other, so potentially these drugs could be used to treat SARS-CoV-2 as well, right? So this is kind of a intuitive idea why we can use knowledge graphs to make predictions, to make reasonable predictions for drug repurposing. Okay. So you can see that essentially we want to make predictions on the, or you want to predict the links between the drugs and the disease. So even more fundamentally, we're actually trying to do reasoning on top of the biometric knowledge graph, or essentially link prediction on any kinds of knowledge graph. So in my group, so we have been working on a bunch of techniques for reasoning on knowledge graph or link prediction on knowledge graph. So including more traditional methods based on knowledge graph embedding methods. Basically, for knowledge graph embedding based methods, so we're gonna predict, or we're gonna map each entity and the each relation as a vector, basically into the continuous space, and then we can, for example, measure the similarities between the drugs and the disease based on their vectors, right? We can calculate their cosine similarity so that we can do link prediction. So this is the first type of approach we have. Okay, the second type of approach we have been working on is based on traditional symbolic logic rule reasoning, right? Because as I said, there's some logic rule we could leverage. For example, if a drug is able to treat a disease, and this disease is similar to a new disease, then the drug could be potentially used to treat this new disease as well, right? This is one type of rule. So another rule could be let's say this drug is able to block this protein, and this protein is a causal gene or causal protein of the disease. Then potentially this drug could be used to treat this disease, right? So there are many such kinds of logic rules we can leverage for symbolic logic reasoning on knowledge graph. Okay, so this has been studied quite a while. So what we've been working on is trying to combine the symbolic logic reasoning methods with deep learning methods, and this is one type of approach we've been working on. Okay, So another type of approach is like, for the kind of like logic rules I just mentioned, maybe like for some new knowledge graphs, we actually don't know all the logic rules, right? So then the question is, are we able to automatically discover the logic rules from the knowledge graph? And then we can leverage those logic rules for link prediction or for reasoning on knowledge graph, right? So I think a big advantage of using logic rules for reasoning on knowledge graphs is that like, so they are interpretable, right? So basically they tell you, okay, why you make this prediction, right? Because they will tell you that the path, the logic rules they use for making the prediction. So this some work we've been working on in this space, and very recently in this year's Neurobase, we also develop a very general graph neural network for link prediction on any kinds of graph. So this algorithm is able to achieve like a really state-of-the-art performance pretty much on all kinds of like graph data set. Okay. So finally, actually, we sort of like assemble all our efforts in this space into a new system called like TorDrug. So TorDrug is basically an open source machine learning framework for drug discovery based on a bunch of different machine learning techniques, including graph machine learning, such as graph neural networks, geometric deep learning, and the knowledge graph representation, or deep general models, reinforcement learning. So our goal here is really trying to like facilitate the research in this space by like for example like really trying to minimize the domain knowledge people need to have if they want to work on drug discovery. For example, for machine learning people, maybe they want to work on drug discovery, right? But they don't know which problem they can work on, right? So here we provide a bunch of like different tasks, data sets. So we do some benchmark. So for machine learning people, they can really focus on developing machine learning algorithms instead of like they don't need to worry about like the data sets or the evaluation metrics. Okay, so these are the goal of like our TorDrug system. So here actually we already provide like solutions or benchmark a bunch of different tasks, which is actually some all the tasks I just mentioned: property prediction, self-supervised or pre-trained molecular repetitions, de novo molecule design optimization, reaction prediction, and also retrosynthetic prediction, mathematical knowledge graph reasoning with applications in drug repurposing or target identification. Because for target identification, essentially try to put links between the disease and the genes, right? And now we also work on like big molecules like proteins, and these are some areas we've been really actively working on. So these are all the students who and also advisors who contribute to this project. Okay. So finally, I also want to mention like a little bit like what we are working on. Okay, so you can see for all the work we've been working, all the work I just mentioned, I just introduced. So they are all based on like graphs, right? You represent molecules as a graph. However, like actually for molecules, more like a natural and also intrinsic repetitions of molecules is their 3D structures and their 3D conformations, because the 3D structures or 3D conformations determine their biologic and the physical activities. And so now we are really working on like developing like geometric deep learning techniques to model like small molecules and proteins. For example, use geometric deep learning techniques to extract the geometric features from the surface, which is very important, like for example, protein ligand, protein interaction modeling. And also now we are also very actively working on like a big molecule design, like a protein and antibody design. So here there's a really huge opportunity there, because now we really have a lot of data in this domain, like thanks to the like a next generation sequencing or synthetic biology, right? So we are able to sequence the protein sequence and also synthesize protein sequence, which are able to generate a lot of like data. And now we also have like a very accurate protein structure prediction, or even like a protein-protein interaction modeling to like AlphaFold 2. So this basically provides really a lot of like opportunity out there. Okay. So with that, I will stop here and maybe take some questions. Thanks very much.
Thank you, Jan, for this excellent talk. There are some questions on the chat. Maybe we can start with them first.
Yeah.
At least the one that you didn't respond during the talk.
Right. In molecule generation results, what is the size on network use? I'm not sure what do you mean, like
I guess the number of nodes of your graph.
So that's pretty much like is the same as the number of like atoms in your molecules. So we use a zinc 250K data set, like the maximum number of atoms is 38. Right? And the second question, to download your TorDrug, does it require any special hardware or just like a i5 desktop is sufficient? I mean, of course, you can download TorDrug in your desktop, but if you want to do training, I think maybe your desktop is not sufficient, right? For example, you want to pre-train a molecular reputation on a really large number of data sets, you probably need to have a server. Yeah.
Other questions from the participants? Well, let me start with, I have a couple, but I can limit myself to one or two. Let me start with your last slide. So I totally agree that this type of data, protein, antibody type of networks, they are extremely interesting and one of the most promising fields for this type of techniques, I guess. So, but though they come with a lot of challenges, and one of their challenges is related to the dimensionality. Because if you think of cells, proteins, etc., then you can have billions of cells. I mean, you can have graphs with very large size. So, what is your comment on that? Have you how do you see this method scaling, and have you worked in that direction?
Yeah, so we are doing some work on this. Yes, I think it definitely is in terms of like computational complexity. I think it's definitely more expensive than small molecules because like for proteins, like it's pretty big, right? And then so I think so there are a few different ways. That for example, for proteins, if you work on the residue level, the graph is not that large, right? So it's still durable. But of course, in some applications, you may want to like work on the more like atom level modeling. So I think in that case, you can do some like subsampling. Basically, you crop like a part of the protein. Yeah, I mean that's actually some techniques also used in AlphaFold 2 or even the Rosetta 4 developed by David Baker's group in Washington, right? So they also have like similar because some of the proteins are too big and they cannot like store the proteins in the GPU memory. But then what we can do is like we can just like a model in every iteration. Oh, we can for each protein we can just sample a part of the proteins, right? Which is durable. Yeah. Yeah. But of course, it's definitely much more complicated and also more computation expensive than small molecules.
There are two more questions. So probably To, I don't know if you want to unmute yourself.
Okay, sure.
Yeah, sure. Yeah. So my question. So first of all, thanks for a very nice talk. So actually, I have a question about the first problem that you described about like using the maximizing the mutual informations. So you mentioned about that one of the challenges in this problem is the lack of a labeled data. And I'm actually wondering if you can elaborate a bit more on how your approach can alleviate the problem.
Right, because in this case, like we are trying to learn the molecular reputation based on label data, right? I mean, this is pretty much like a similar idea, like what have been going on in the natural language processing domain, right? So you're gonna pre-train the models based on large number of like on label like text data, and then you can just like then fine tune your model based on a very limited number of label data. And here we are basically doing the same thing, but then the question here is how can we learn a pre-trained molecular reputation based on a large number of like unlabeled molecules, right?
So is it somehow implicit in the objective function that you proposed it?
Right. Yeah.
Okay. I see. Okay, I see. I saw again what you mean. Okay, I see. Thanks.
And there is another question about knowledge graph. I don't know if the person wants to unmute himself or I can read it. So do you recommend any public data set that can be used to start working with knowledge graphs, basically?
Right. So for knowledge graph, like reasoning or link prediction, there's some like standard benchmarks. Actually, in all the papers, we use the standard benchmarks. So you can refer to these papers. Yeah. So those like there's a pretty standard. So basically, all people work in this domain, they will evaluate their algorithms on those standard benchmarks. They're not too small, but they're not too big.
I have a question. Is it can you have multi-objective using your algorithm, your network? Is it can you have multi-objectives?
Yeah, I mean, so this is basically related to like, I mean, how do you want to design the rewards, right? I mean, here, if you have multiple properties, or you can just like integrate those properties into your final reward, right? So yeah, I think this is basically related to how you want to define your reward. Yeah, definitely, it should be durable, right? I mean, a simple approach, you can just like take summation or take the product of the two properties, right, as a reward.
Okay, thank you.
Any other question? If not, maybe I can ask a last one that is related to, you mentioned a few times in your examples about causality. So how do you exactly achieve causality with this type of frameworks?
Oh, actually,
so yeah, it was in this drug repurposing part.
I think we mainly use like some causal information to make predictions, but I think most of the predictions we make, I think it's more about correlation. I think we cannot like establish causality in our framework. This is not our focus.
Okay.
Yeah.
Okay.
But of course, it's an important problem. I do agree, and then there are quite a few people at the MENA who are working on this. Yeah, it's now there's a growing interest in the intersection between causality and machine learning.
I have a question. I'm not sure if I missed it when you were explaining, but sometimes RL seems to have not do very well in diversity, generating diverse molecules. I'm not sure if I missed this part. So.
Oh, right. So I think there are also some diversity metric we didn't evaluate. Right. There's some diversity metric I think later people developed. Yeah, I totally agree. So we can definitely evaluate on those. Although I think at that time most people didn't evaluate with this metric. Yeah, but later there are some latest paper they did like evaluate the diversity of the genetic molecules. But I think in practice, actually, according to the examples we have, actually the algorithm they're able to generate very diverse molecules.
Okay, thank you so much for clarifying.
And this question, I wonder how will you evaluate the heuristic of generating structure if they are new and unseen? Yeah, so here these are the kind of metrics we use: validity, uniqueness, novelty, right? But in practice, I think we can leverage more like some chemical metrics to evaluate the heuristic of the generated molecules.
If I might, I just want to add a follow-up question for that. For the uniqueness, I wonder how you would say the uniqueness. You mean how closely this structure is to the original structure, or
it basically means like uniqueness means like whether the molecules generated by the model, they are different from each other. Yeah. So if there's an atom or an bond difference, so then they are different from each other.
Then the novelty would be what? It's harder to see how you compare to structure, and then you would say uniqueness, novelty, and the reconstruction. If it's just for a graphical structure in general, if you haven't seen them, how would you know their novelty and whether or not that they are actually unique?
Oh, unique is just like if you just compare to molecules, right? So if they're atoms and the bonds, if they are different from each other, then they are a different molecule. And
so it's not the structure-wise. It's not like the whole structure you're comparing. You're comparing only
the graph. Yeah,
okay.
The graph. We only compare the graph, right? And for novelty, you just like basically you want to know like whether the molecules you generated they're different from training data, because otherwise we can just like copy the molecules from the training data and we can satisfy all the other metrics, right? So we hope like the algorithms are able to generate molecules which are different from training data.
So will there be a trade-off between the uniqueness and novelty?
Not really. I mean, because the algorithm are able to pretty much always generate like a new molecule, molecules that are different from the training data, right? But then we can also make sure that those molecules are different from each other, because the reason is like the space is pretty large, right? It's very, very large. So actually, it's very rare that you are likely to generate like two basically almost the same molecules, right? So you think about it, the chemical space, it's very large. So it's very rare you generate the totally same molecules.
Okay, thank you.
You can calculate the probability. It's pretty like really like pretty much it doesn't happen at all, right? And that's also actually why we need to use machine learning, because actually the entire chemical space is pretty large, and then so we can use machine learning to search the kind of like a space that could like that are the most promising. Yeah.
Okay, thank you.
Thank you.
So many interesting questions. I would say that probably we can resume, and then if there are any additional questions, I'm sure that Jian would be happy to get them through emails or everything or anything. So thanks again a lot for this very interesting talk. Thanks everyone for attending today. And so this was the last seminar for this year. We will resume next year in January with 2 talks from Peter Battaglia and Michael Bronstein. We will announce the details, I guess, later this year or early January. So thanks again, and happy holidays to everyone.
Thank you. Bye-bye.
Thank you.